So most of you have heard of it or even own the card. So for me, it's kind of difficult what to do. I mean, presenting the card, how to use it probably wouldn't make sense. So I decided to give you a bit of insights, how the card works and how I developed it. So it's going to be a bit technical. So there are two FROMs by now. FlashROM was last year. That was my first card that I did. And the FinalGROM is now the successor card. So it's like an improvement in basically all aspects. The most obvious reason is it has more RAM. So the FlashROM had 4 banks, total of 32 kilobytes, but the FinalGROM has 128 banks, meaning it's 1 megabyte of RAM. So currently the largest known image, at least that I know, is Don't Mess with Texas. You can fit it in twice here. But these banks are also special. So every white square here is a bank. And you can see, so first of all, the last 8 banks can be configured as GROM, but only the last 5 are used. So these are the system GROMs. You cannot override them or use them by default. And these are for the cartridge GROMs. And then each ROM bank can also be configured to be RAM if you want, at least half of them. So you can have ROM, you can have RAM, and the GROM can also be RAM. So you basically configure it per image by setting the 4th byte in the image. It's all documented on the homepage. But I just wanted to point out, so you have ROM, RAM, GROM, and GRAM if you want. Some other improvements where I added folders, but I kept the 171 limit for the number of entries per folder. I'll come to that later. And you can have up to 10 levels of folders. So you probably can't fill an SD card because there aren't enough images available. There's an integrated help viewer, but right now it's not really used. If you downloaded my zip file from WH Tech, I put help files for my own tests, but then the community has to supply the other help tests that you can activate in the FinalGROM menu. And then there are some special features more for developers. You can reload images. So if the one image is running and it's out of space, then it can reload another image, just like Extended Basic with the run command. And you can write back your image back to SD card. This is especially useful if you have RAM in your image, because then you can change the RAM and write back the changes. For example, the high score, or your current progress, or your preferences, anything like that. Now, how do I came up with this idea, or how do you get there, basically? So just a quick introduction here. So this is the easiest cartridge that you can have. You just have one ROM or EEPROM in the middle, and that's it. And this EEPROM is connected via these connectors to the bus, and that's it. So main idea is to replace this ROM with some RAM, then just add an SD connector, and then you need some controller that will load whatever is in here into this RAM. And you don't have to do anything with the access of the TI with that cartridge. But there's a problem. It's a bit small, I hope you can see it. So this is the cartridge with the RAM chip here. And then you have here the controller that reads it, and this controller is connected to the RAM chip here. So this is okay. But as soon as you see the whole picture, you see immediately that the CPU has this large bus, and the bus is connected to all different devices. So this is the main system, this is the RAM expansion, the disk controller with the drives, and they are all connected through this bus. What they have additionally is one select or enable line, so that the devices know who that the CPU is talking to them. And the cartridge has one as well. But if the controller writes to the RAM while the CPU is talking to some other device, this data goes in here as well. And there's a conflict if the controller writes it at the same time, not honoring this one. So you have to have some mechanism that schedules this dual access. And what I did with the FlashROM was I had basically a gateway that would take the cartridge offline when the controller loaded the image into the RAM. And you can see this gateway up here. It consists of these 3 chips. It basically just prevented any electrical connection when the controller said, okay, now block, and then you could re-enable the access so that the TI via this controller could read the RAM. That was the basic idea for the FlashROM. And I kept it for the FinalGROM. So you see the same components. This is here the controller that reads the SD card. It's a bit smaller. This is just for programming. Then you have the RAM. This is now much larger. And everything else is in here. So this is the main component. It's a CPLD. I'll come to that later. But this overall structure is the same for both cartridges. This is a schematic overview. So you have this CPLD in the middle, which is responsible for all the logic. And then to each side you have the actual SRAM, which contains the image and also the menu in the beginning. And on the other side you have the microcontroller, which acts like the manager of everything here. This one is also responsible for accessing the SD card. But you can see, or actually, and then here we have the CPU, and this represents the bus. So the bus also goes to the card, and then it's only connected to the CPLD. And as you can see, all access is through the CPLD, so this sits at the center. The microcontroller cannot write to the SRAM directly, and also the CPU cannot see the SRAM directly. Oops. So now, how does it work? A new component on the FinalGROM is on the left upper corner. It's a voltage converter. The problem is that all of these components, except for this one, runs, well, there's an option, but so on this card, everything runs at 3 volts, whereas the TI runs at 5 volts internally. So in general, you cannot just connect them. I won't go into the details here, but there's certain levels defined, so what is considered low and what is considered high in terms of voltage, and they have to be compatible. And the problem is basically that if the TI is sending to the cartridge any signals, it'll send at up to 5 volts, and this is too much for the cartridge in general. So you have to usually employ signal or logic level converting. But in this case, we're lucky because the CPLD I used is 5 volt tolerant. So even if it runs at 3 volts, it can accept 5 volt signals. So I don't have to use any logic shifting here. Now, the first part that you see of the cartridge is basically is the menu. It's always the same, but the entries here are different, so it depends on your SD card. And how is this built? So a lot of components are involved. In the middle you see the 8K used for the menu. So this is the RAM on the card. It uses only it only uses one bank for this. So first, the microcontroller will write the fixed menu code into the RAM. It has to start with AA so that the TI can recognize it as a cartridge. And the fixed code uses 800 bytes. So this is always fixed. And the entire rest of the cartridge is filled by the entries. So the microcontroller will look at the SD card and it will look at all the files that are on there. First, it will check the file name, so it always has to end in bin. And then it will look inside and see if the first byte is AA. Because if that's not the case, it's not a cartridge image. And also, it ignores files ending in D, because that's usually the second bank, which has a copy of the menu of the C bank. So that's just skipped. Yeah, and if it's a G file, it also has to start with AA. Well, it might not start with AA, but this entire menu might be further down at some other bank. So it has to scan the entire file for a G file. Then, so if it has all these, or actually for each of them, it writes 32 bytes into this menu here, containing the file name, the display name, the start address, and the type, basically. And this is actually the limit that you see. So this is the variable RAM. So it means it can store up to 176 images. And I rounded it down to 171 because that's basically 9 screens of, I don't know, 20 or so lines. And of course, right at the beginning and right at the end, the microcontroller has to tell this gateway here to block the access and to enable the access again. What I haven't shown here is the CPLD, because it would complicate this picture a bit. For the menu entries, as I said, it has to look inside. So always the AA to signify it's a cartridge image. Then at this point here, 6006, is always the start of the menu chain. So this points to this address, this points to this points to this and here, and 0 denotes the end of the chain. And so after each of those here, you have the start address, noted here in pink. Then you have a length byte, and then you actually have the name of the entry here. So this is the bytes, here it's in text. So you can see we have DB and help, sort, and so on. And you also see that we have obviously 5 entries here, but only 3 of them are linked. So some are hidden, probably not implemented or something like that. But the FinalGROM looks at this structure and then uses these names to display in the menu. So it doesn't matter what file name you use, you'll always end up with these defined names here. That's fine for individual images, but when I put together my large zip file with a lot of TI programs, there are some problems. So this is a sample menu that could happen. You see, for example, here you have entries Parker Brothers game twice, whereas in fact it's Frogger and Hubert, for example. So Parker Brothers just didn't tell you when you run it what's the game name. So this is probably bad if you have a large collection. So what I did, I hacked the menu, meaning basically that I overrode the name with the actual name. Then what can happen is here, so you have entries like English, Dutch, Italian, German, whatever, which is also bad because you don't know what program it is. But some programs just give you a language menu where you choose it. So what I did here is I took the English one, replaced it with a better name, but it had to fit into these 7 characters, so it's a bit compressed. And then I just chopped off all the other languages. And then you could still have duplicates here, like parsec, maybe just because you have 2 different file names, but they both contain parsec. So these things can happen. What I also discovered is, like some programs, for example, the video chess in German, TI-Treff, just wouldn't work. And when I looked into it, what happened is, so when you run the actual cartridge here, you see the title screen, but when you go to the menu, you see that it implements its own menu. So basically you select it and it goes back to the TI and then the program runs. But the FinalGROM just sees an auto-starting image. So it would basically run this, but then the return back from GPL to the TI wouldn't work. So what I had to do is I cut off this menu here because it doesn't really provide any value. So I cut this off and just use the regular menu to start the Schachmeister here in this case. So for the zip, I had to actually clean up the menus quite a bit to make it useful. Now, let's come to the heart of the cartridge, as I said. It's a CPLD, which means Complex Programmable Logic Device, which is an older and much smaller device than an FPGA, what Eric has told about. It has combinatorial logic, which means you connect ANDs or ORs like you would with chips you put together. And it also has process logic, which means that you're using a clock or react to some rising or falling signals. And this basically gives you things like flip-flops. The CPLD is very limited. You have 144 macrocells. So FPGA would be in the tens of thousands. But these things give you things like flip-flops from those registers, latches, counters, adders, comparators. But you cannot do a lot of logic with those. But for the FinalGROM it was sufficient. It doesn't run without a clock, which is a bit debatable. So people say you always have to have a clock. This doesn't. And since it doesn't have a clock, I looked at the response time and the maximum was this. So you could say it runs at about 38 megahertz. And coincidentally, so the at least my CF7 Plus uses an older version of this one, which runs at 5 volt instead of my 3 volt, and it's much smaller. So it's a fourth of that in terms of capacity. Now the CPLD handles all the signals basically. Remember, it's set at the center, so it was connected to the RAM, to the microcontroller, to the bus, and So in the beginning, something is loaded. Either it's the menu, or it could be one of the selected images. So to load something, the CPLD basically shuts off the TI bus, or the connection to the TI bus. So this is red here. But it puts through the microcontroller. And then the microcontroller reads whatever it's on the SD card, and this goes through the CPLD to the RAM. So this is loading without the conflict if the TI read the SRAM directly. Then the second step is, so once the image is loaded, the microcontroller tells the CPLD now run. And in run mode, this connection is severed, but now the TI goes through the CPLD to the SRAM. And depending on what the TI wants to read, it could be the ROM, it could be the ROM that's actual RAM, or it could be one of the GROMs, which resides at the bottom of the RAM. So this is the usual case, loading and running. But there are also some special cases. For example, while running, it can do bank switching. Bank switching happens when you write to the cartridge address space. And then the CPLD will just select another bank. Or when you want to do image selection, the TI basically has to talk to the CPLD. And it can't actually talk, but what's happened is the CPLD watches the TI bus for bank switches. And if you switch banks in a certain pattern, the CPLD will recognize a character. And a stream of character tells it the file name that should be loaded here. So basically, the CPLD will tell back to the microcontroller which image to load. Now this is what VHDL looks like. Eric didn't tell. I won't go into details, I just wanted to tell you these are basically the in and output pins of the CPLD. So here's the TI bus. You recognize ROM selection, GROM selection. Here's the data bus, the address bus. Then we have the connections to the RAM, also data and address bus, output enable, write enable, and this is the command connections to the microcontroller. And then with that, you have these, this is the plain logic. Basically you want to say, so this is the data bus to the TI. So we want to say put out, well, RAM, DX is the RAM data bus. So put the RAM data bus on the TI data bus when we're in action running, when the ROM signal is low, and the data, no, it's not database, data, we're reading data in any case, then we're doing this. We're doing this also if we're running, the GROM select is low, we're reading data, and we're in the current GROM bank, and so on. If none of this happens, we're not sending anything. So this is like high impedance, or if it's a bidirectional, it just means read something, and so on. And of course, this RAM-DX has to be defined somewhere else, so it's down here, and so on and so on. And the other way to define this is to define a process. So the special thing here is you're acting on some falling or rising edges. It's like a trigger. And again, here's the process for the GROM, so it's GROM emulation. This is the initialization. And then you have the cases set GROM address. Further down is read or write data. So it didn't implement the read address because the TI does it automatically. So I won't go into any details here. Now I just want to show you some photos of the process, how I built it. In the beginning, of course, is always the breadboard. So here is just an EEPROM that contains a ROM program, so not a GROM. I basically had to start from scratch again here. So this is fixed. Here you see basically a breakout board for a CPLD. So here's the CPLD, and it just puts all of its pin to the sides so that you can connect wires to it. There's a little reset button and that's it. And here, that's an Alpine cartridge where I severed all connections and then I soldered cables or wires to the connector so I can use it as an interface. So basically you plug it into the TI and then the wires carry all the signals with Alpine not running. And with that I try to run this program in the EEPROM, but as you can see it didn't work at first. But then after some debugging and so on and rewriting the VHDL code, it eventually ran. You can see it's a bit shiny here. So this is the program in this EEPROM here. So the first step was taken, so I saw that I could actually run a program through the CPLD. But for the next step, the breadboard wasn't really suitable, so I had to get a PCB, a professionally made PCB, which looked like this. It's all through-hole, except for the RAM and the CPLD, which isn't available in through-hole. At that point, I really wanted to do through-hole as much as possible. And up here is the voltage converter. And maybe you can imagine that this is a very stupid layout because the voltage converter is very high, so you couldn't actually insert it into the TI because the voltage converter would block it. But other than that, so that's pretty much like the final design, except that it's all through-hole. Now for the SMD, I had no experience in soldering SMD and I was a bit afraid. So I got a stencil. It's basically a large aluminum sheet, and here in the middle you have tiny holes that corresponds to the pads on your PCB. I have no idea why it is so large. But with that, I thought I could use a reflow method to solder. So here's a cheap Chinese reflow oven, which is just a toaster oven basically. And what you would do is you take the PCB, put the stencil on it, put some solder paste on it, and just let it bake in this oven for 10 minutes. I did it once, but the result was really poor. So I resorted to manually soldering this SMD. I wrecked 2 boards, but then it worked. And with this one, I almost got it. So this is with the GROM emulation now working. It was almost okay. But it's really difficult to work out the problems because it's a black box. I cannot debug it or look at it. I only have a scope I can attach to the wires. And what you usually do, so this is the development environment for this VHDL programming. You can simulate. So basically, you have your program, it's finished or it's compiled, and then you define another program that simulates the external input. So you say, ROM select goes high, then wait 2 nanoseconds, then it goes low. And this one did work, so there were no more instabilities. And in hindsight, I assume it was the voltage converter. Maybe the voltage wasn't stable. So this is the third one, and the final board, I thought. Again, I did some changes. I did everything in SMD except for those components that had to be through-hole anyway. So I soldered it together and tested it. And I noticed, okay, it wasn't correct. 2 wires were mixed for the programming controller. So I had to cut 2 here and solder 2 extra wires. So it's good that I tested it, so I could correct it, and then I had the right board. But I also, since I wanted to make a lot of them, I figured I can solder them by hand, especially with SMD. So I wanted to order pre-assembled boards. But the problem is, even though I had the cartridge now, I had never ordered assembled boards. And when you do a PCB board, you send a bunch of files, Gerber files, that tells the manufacturer where the traces are, where the holes are, and so on. For assembled cards, you need an extra file which tells the pick-and-place machine where to put the components and which orientation they are. And I never had done this, and I didn't trust my program, so I just ordered 10 assembled boards as a test to see if they work at a huge price. And this is what they are. So they worked. I was quite happy about that. And this is the final design, or almost. There are 3 differences. Can you spot them compared to the final board, if you have one? One is very obvious.
One reset button.
Pardon me?
There's only one button for reset.
Yes. Well, I didn't solder the button, but there's only one button here. So I added a second button that resets the TI for the final board. 2 more things. One is actually quite obvious. Well, the second thing is it's lacking the SD connector. So at that point, I still imagined I'd use this daughter board that I used for the FlashROM, which would upside down sit on top here. But no, so Jim Brain from the US buggered me basically and convinced me to use an SD card connector. And the third change is kind of subtle. Here's a power connector. I removed that because the power is also present here. So I didn't need that. Okay, so I made the changes and I ordered cards which arrived. And so this is the final card as we know it. Yeah. Now before I close, I'm almost through. I just wanted to show you 4 specific problems that I had to solve. The first one, when I wrote the original menu program, it was a assembly program, as I used on the FlashROM. But then someone pointed out that QI consoles or 2.2 consoles can't use or can't see ROM cards. So I thought, okay, I make a GROM card. But instead of rewriting the entire menu as a GROM program, I just wrote a small wrapper around it. So on the ROM side, usually there would be the header here with AA, 10, 10, and so on. So I removed it here, just kept it empty. And instead, I had an additional GROM program that would have a header. And then the main so this is the menu entry, and the main program would just do an XML 7.0, which is a jump to assembly. It's looking at a table, so this 7 looks at a table at address, at ROM address 6010. So I had to have a table here at 6010 that would point to the actual ROM program. And the 0 says take the first entry. So basically it just jumps from here to here, and this tells it to jump to here, and then the normal program continues. So I just wrote a small wrapper around the program I had to make it compatible with QI consoles. Another thing is this reloading. As I said, you do bank switching by writing to 6000, and then this byte is basically the bank you want to load times 2. And I also use this for communication. So you write 6000, then 7000 XY, where XY is the byte you want to send, and then again 6000. So that the card will know then the byte is complete basically. So you alternate always between those. And the selection is basically the file name to load, then the type, although that's not strictly needed. Actually, it is needed. And then some random data that's historical. I actually don't need them. And the reloading is basically like an exception, like a selection when a program is already running. Of course, the menu is also a program that runs. But when I have, say, Pacman running, and Pacman wants to load another program, Pacman has 2 banks, so it does bank switching a lot. And this bank switching actually works. So Pacman doesn't use address 6000 and 6002. It actually uses all kinds of addresses. So this can be random. Just the last bit is basically looked at. So that means if a program is running and does bank switching, there's a lot of noise. So it basically looks like to the cartridge like this. And it cannot tell, should I load this weird named program or should I wait until, well. So what I did, I introduced a special sequence. So this is the byte 99, this also. And then it has to send, okay, FinalGROM99. So whenever the cartridge sees this, then it knows, okay, now comes the file name that I have to load. So by this sequence, it can tell the noise from the file name. And there's a very small probability that random noise will contain this sequence. Another thing is the file, the help viewer. Again, I use the sequence here. So this is only sent by the menu. So it sends, again, this OK sequence, then the file name, which has to be the same for both, and then a special code 02 in bytes that will tell the FinalGROM, okay, now I need to load the help viewer. So it'll see that, and then it's loaded. And this one, to go back, just has to send 1 random byte. And then the FinalGROM knows, okay, now I'm going back to the menu. And I had to actually move around the data that I store in Scratchpad RAM quite a lot. So that, I'm not sure if you notice it ever, if you use it ever. But if I'm somewhere in a folder at some, say, page 5, the actual state is reconstructed here when you quit the help viewer. So that took actually some work, so that you're not starting at the beginning again. And then dumping also uses this escape sequence basically. In dumping, so the CPLD basically reverses things. So it reads the contents of the SRAM byte by byte, forwards it to the microcontroller byte by byte, and this will write it back over the currently loaded file pipeline. So you cannot use that for GROMs. It has to be a ROM program, and it has to be a single file for technical reasons. You also cannot create new files for technical reasons, so you're basically overwriting the image or the file that you're currently using, but you can do it differently. And to indicate, so if you're writing a program and you want to do that, you just have to send the sequence, these X's don't care, and then 0 and 3, and this indicates, okay, now dump the contents of the currently running program back to SD card. For example, if you want to save your current progress.
One question on that.
Yep.
Could you theoretically choose an existing image that has 8K of memory or uses 8K of memory and inform and change the header so it thinks it's 16K of memory and extend the file size basically with zeros and then write just to the second 8K so that it's kind of like a container?
In a way, yes, you could do that. So you cannot increase the size of the file, but you don't have to write everything. But you also have to start from the beginning.
Okay.
So you cannot just write the second header. That's not possible. Well, it is possible. It's just not implemented. So it was meant to save the entire image in memory. But it knows how much of memory is filled. So if only half of it is used, it only saves this half. All right, that was actually my last slide. So if you have any questions, I guess it was a bit fast and a bit technical, but that was actually my purpose. So if you have any questions, let me know, please.
Just a comment on the UI consoles.
Mm-hmm.
Also the 994, the original one, 994, has no search for only ROM files, and also the 998. So it's also like, by adding that wrapper for the GPL, you added support for those for your module actually.
And actually another comment, so since the menu is GROM and visible, you can even start a ROM program on a QI console through the menu. So it's not just that you can run the menu, but actually ROM programs that you couldn't run before. So, yeah. All right, then thank you very much.